Hey guys, I'm Mr. Bison. I've been a maths teacher for the last 10 years, and in today's video I'm going to be teaching you about differentiation for A-level maths year 1 and year 2. Now this video is going to take the format of me explaining some of the concepts as well as doing some example problems. So if you want to follow along, you can go to the link in the description to download a blank version of the PDF, and there's also a filled-in version there too. There's tons of other resources in my Google Drive, so do make sure that you have a look in there as well. If you haven't visited Bison Maths before, welcome, but also go to my channel homepage. You'll see so many videos that will help you with your maths, whether they're revision videos or actually just tutorials that take you through the whole topic. So without further ado, let's get started on everything you need to know for differentiation. I've split the PDF into two parts, so you've got differentiation for year 1 or year 12 and then differentiation for year 2, so you can just watch the parts that you need. So it's a pretty tricky concept to explain, but we'll do our best to do it as quick as possible. So let's just talk about some terminology first of all. When you differentiate a function, what you actually get is something which is called its derivative. And the derivative of a function tells you how it changes, and it's often called its rate of change, or it is frequently called the function's gradient. And we're going to try and explore these throughout this whole video. A quick little note about notation. If you see something like d by dx, this means to take the derivative or find the derivative of a function with respect to x. Of course, it doesn't have to be x down here, it could be with respect to other variables. And just to introduce this for a very simple one, if you d by dx y, you by definition get something called dy by dx. And this in itself is an example of a rate of change. So let's just have a look at these examples of 4 rates of change and see if we can explain a bit about them. So I've said here, in other words, the rate of change says how the top variable is changing in relation to or with respect to the bottom variable. So this first one I've got up here, which is dp dt, it's explaining how the population of, I don't know, maybe some animals is changing with respect to time, which is measured in years. So if dp dt was something like 300, it would be saying that the population was increasing by 300 every year. The velocity of a car could be measured in relation to the amount of time that the car is travelling. And if the velocity is changing with respect to time, we would say that it's accelerating. You could also have things like dA by dr, where maybe A represented the area of a circle and R is the radius of the circle. So how is the area going to be changing as the radius is either increasing or decreasing? And then last of all, dy by dx is probably the most common way that you might see a derivative, which is saying about how the y coordinate is related to the x coordinate, which should make you think of the second version that we can think of derivatives, which is how y is changing with respect to x, in other words, the gradient. So I want to explore this gradient concept a little bit more. Now, normally when we think about gradient, we think of straight lines, and to find the gradient between two coordinates, we usually do y2 minus y1, so you subtract the y coordinates, and then you divide it by the x coordinates. So you can already kind of see a bit of this similarity between the change in y and the change in x. And that's literally what this dy dx means. It means the change in y divided by the change in x, d actually standing for that little change. Now, the whole point of differentiation is to try and find the gradient at a particular point on a curve. So I'm really trying to, in this example, find what is the gradient at this place here that I've marked with an x. And you can see that the x coordinate is x here, and the y coordinate is f of x, the output of that function. Now, I can't just dive straight in and find the gradient at this point, but what I can do is instead find the gradient of a line and then use this kind of GCSE definition that I've got here. So the way that I do this is I say, okay, well, let's try and just add on a tiny little bit to the x coordinate. Let's just add on h to be able to get to that part. Well, then the y coordinate is also going to change. So the input is no longer x. I'm putting in x plus h inside the function. And the idea with this is to try and use this formula to come up with what the gradient of this dark red line will be, and then to make the gap between x and x plus h get as small as possible. In other words, to make h become 0. Now, you can't just go straight in and have it as 0 because you would end up as dividing by 0. So let's have a look at this thing down here, which is first principles, and see how this might come up with our formula. Quick little side note about notation, you'll see here that dy by dx can also be written as f prime x, but I often just call that f dash x. Okay, so we said we were going to make h become 0 slowly, and we were going to try and find the gradient of this dark line. Well, the change in y is going to be f of x plus h minus f of x. And the change in those x coordinates that we've got there is actually just the gap between them, which is just h. So you can see now why you can't just make h become 0 immediately, because you would be dividing by 0. The last thing we add here is that there's a limit. This limit is saying that you're going to take the value of h and you're slowly going to make it become 0. This probably sounds really abstract, so what we're going to do is try and apply this formula for first principles to a particular function, and we'll see how that goes. This, I must also add, is in the formula book. So here's our first problem that we're going to have a look at. We're going to find from first principles the derivative of 2x cubed, and then we're going to try and find the gradient of 2x cubed when x is equal to 1. So I'm going to start off by saying that my function in this particular case is going to be 2x cubed, and then what that means is that f of x plus h would be 2 of x plus h cubed. So to find f dash x, or the derivative, it's going to be the limit as h approaches 0. This is just using the formula from the other part of the page, which is f of x plus h minus f of x, all divided by h. Now each time I'm going to have to write at the beginning the limit as h approaches 0 until I actually take that limit. So I'm going to start off by having two lots of x plus h cubed minus 2x cubed, and that's all going to be divided by h. Now using binomial expansion, we should be able to expand this x plus h cubed here. So that's going to be the limit as h approaches 0, two lots of x cubed plus 3x squared h plus 3xh squared plus h cubed, all minus 2x cubed, and that is still going to be divided by h there. Now you should hopefully be able to spot that this 2, when it's multiplied by the x cubed, is going to cancel with this 2x cubed here, so I can get rid of that part. And then when I expand the brackets, I end up with the limit as h approaches 0. I get 6x squared h plus 6xh squared plus 2h cubed, all divided by h. Now I'm really nearly there. I can actually divide everything by h as well, so that I get 6x squared plus 6xh plus 2h squared. Now we can actually take limits, because as h goes towards 0, and I'm no longer dividing by 0, so this is okay to do, I can also say that 6xh would become 0 because it's multiplying by 0, and 2h squared would also be equal to 0. Hence, we can see that f dash x, the only part that's going to be left is this 6x squared that we've got here. So we can say that f dash x is equal to 6x squared. That was part 1 of the question, and part 2 of the question just wants us to find out the gradient of 2x cubed when x is equal to 1. So this just means that I can substitute x equals 1 in here, and so the gradient would be equal to 6 multiplied by 1 squared, which is 6. So let's have a quick look at this and see what that means. Well, if I zoom on this graph here, I'm saying that when x is equal to 1, so at this point on the graph, the gradient is going to be roughly the same as, well, not roughly the same as, but exactly something which has a gradient or m value of 6. Okay, so we are saying that dy by dx, which is kind of like the new way of saying the gradient, is equal to 6 at that point. Okay, there's got to be a quicker way though, rather than doing from first principles. So there's actually some shortcuts about how you can differentiate these functions. So let's have a look about how you differentiate anything that looks like this, so ax to the power of n. And it needs to be noted here that a and n can be any real number. They can be positive, they can be negative, they can be fractions, they can be decimals. It just will work for all of them. So let's just go through and see what these things will differentiate to. So if you take the derivative of y with respect to x, we mentioned this one earlier on, it's just going to give you dy by dx. Now, for this one, the pattern that you notice is that you pull the power down so that instead of it just being ax to the n and you multiply, it will become a n x. So this power that was up here, we've brought it down and we've multiplied it. And then the second thing that you do is you take the power which was previously n and you reduce that power by 1. So I'm just going to repeat that one more time. You pull the power down from the top, which was previously n, you multiply it by a, and you reduce that power by 1. So I'm just going to jot that down here. Pull the power down and multiply it, and then you reduce the power by 1. This works only for terms which are exactly in the form ax to the power of n. Quick little side note is that constants disappear, and I'm going to show you why. So for example, 3, if I was going to write 3 in this exact form that we've got here, it would be 3 multiplied by x to the power of 0. Now, when you differentiate that, you would pull the 0 down, so you would have 3 multiplied by 0, and you'd reduce the power by 1 to minus 1. Well, 3 times 0 is always just going to give 0, hence, if you have a constant term, it's just always going to disappear like that. So let's just do a quick bit of practice, and we're going to differentiate these with respect to an appropriate variable. So I'm going to differentiate this first one with respect to x, so that the y will become dy by dx. Notice how I'm applying it to each term separately as we go. X to the power of 5, well, I'll pull that power down so it becomes 5, and I'm going to reduce the power by 1, and that 7 is just going to disappear. I'm also going to differentiate this one with respect to x, so y will become dy by dx. Now the 3 will multiply by the 4 to give me the 12, and I'm going to reduce that power by 1, and that minus 4 is going to disappear. I'm also going to differentiate this one with respect to x. So this time I have a negative, I'm going to do the 2, and I'm going to multiply it by minus 4 to get minus 8, and I'm going to reduce that power by 1, so it's going to go down to minus 5. Now this one looks a bit different because we've got different variables. I think it makes sense, as this is in terms of r, to differentiate it with respect to r. So I'm going to get dA by dr. Now pi is just a constant here, so you can just multiply it like any other number. I'm going to multiply it by the 2 when I pull that 2 down, so that's 2 pi, and I'm going to reduce that power by 1. Interestingly, when you differentiate the area, you get the formula for the circumference. Okay, some different notation here. So we've got f of x. That's definitely going to go to f dash x or f prime x. So I'm differentiating with respect to x here. Now k, we're just going to treat it like a constant. So we can just say 4k multiplied by the power of 2. That's going to become 8k. And I'm going to reduce that power by 1, but x to the power of 1 is just x. I've then got negative half multiplied by negative 3. Well, that's just going to be a positive 3 over 2. And I'm going to reduce that power by 1, so it goes down to minus 4. This time I've got a function in t, so I'm going to differentiate it with respect to t. Now this is actually the same as t to the power of a third, so I'll pull that power of a third down and I'll reduce that power by 1. Now a third minus 1 is minus 2/3. This one here is not exactly in this form of ax to the power of n. So you're going to need to expand these brackets first of all so that we can differentiate it. So I'm going to have the y times the 2y, that's going to give me the 2y squared. I've got 3 times 2y, which is 6y, and minus a y, so that's going to be plus 5y, and then I've got minus 3. Now I think this time, because this expression is in terms of y, I'm going to differentiate it with respect to y. So I'll get dx dy. That's going to be 2 times 2, which is 4, reduce the power by 1, and then 5y, that's just going to differentiate to 5. If you just imagine that's 5 multiplied by 1, and then it's y to the power of 0, so you're just going to get 5 for that one there. You'll notice, though, that anytime you've just got like a 5y or 5 anything, it's just going to differentiate to the number that's in front. So this one looks like it might need a bit of tidying up. So I think I might start off by saying that we've got t to the power of a half plus 4t squared, whoops, all divided by 2t to the third. So I think this beginning part, I've got the t to the half divided by 2t to the third. Well, it's definitely going to be the half from the numbers, and then a half minus a third is a sixth, so that's t to the sixth. Then the next part is going to be a 4 over 2, which is just a 2, and then 2 minus a third, that's 6/3 minus 1/3, that's 5/3. So now I'm ready to differentiate this with respect to t, and I'm going to get that dx dt is equal to a half times a sixth, which is a 12th, and then I'm going to do 1 taking away from 1/6, which is minus 5/6, and then I'm going to do the 2 multiplied by the 5/3, which is 10/3, and I'm going to reduce that 5 over 3 by 1, and 5 over 3 minus 1 is 2 over 3. Last one that we've got here is v, and it's in terms of x, so I think it needs a bit of simplifying to begin with. I'm going to have, to begin with, a 1 over x cubed. Now 1 over x cubed is x to the minus 3, and then I'm going to have minus 5, let's just think about what the powers would be, is x squared over x cubed, which is x to the minus 1, and you've got a plus 5. So I'm going to differentiate this one with respect to x to get dv dx. I'll pull that minus 3 down and reduce that power by 1. I'll do minus 5 multiplied by minus 1, which is positive 5, and then that's going to reduce to minus 2, and then that 5 is going to disappear. Okay, so how can we actually interpret some of these things? Well, remember that the gradient is talking about, that the derivative is talking about the gradient. So if you find dy by dx and it's equal to 0, it's actually referring to something that is completely flat. And we call this either a stationary point or we call it a turning point. So if we have a look on the graph that we've got here, here is a place where the gradient is 0 because it's completely flat. Here is a place where the gradient is 0 because it's completely flat. And this line that we've got running along here also has got a 0 gradient too, okay? If you find out dy by dx and it ends up as being a negative value less than 0, it refers to something which has got a negative gradient, and we call this a decreasing function. So we would say that it is decreasing, or it is a decreasing function. So you can see a section where it is decreasing is this section right here where it's going downhill. That has a negative gradient. If something has got a positive gradient, we say that it's an increasing function. I'm going to mark that on the diagram with some pluses to show that it's positive. You can see this whole section here has a positive gradient, and this whole section here has a positive gradient as well, so they both get a plus. If you though get that dy by dx is undefined, and that's often if you're doing something like dividing by 0, that is actually referring to something with a vertical gradient. Vertical gradients don't exist, we say that they are undefined. So this line that we've got here is an example of a line that's gradient is undefined, and that comes from things being divided by 0. So let's try and think about how we might be able to do something to do with something called tangents and normals of graphs. So on this graph that I've got here, this red graph, I have an example of this blue line, which is a type of tangent. It is a tangent because it just touches the curve at one point. You can see that when x is equal to 1, that blue line is just kind of skimming that red line that we've got there. A normal is very similar, apart from instead of it just touching it at that point, it is perpendicular to the curve at that point. So here is the tangent, the blue one, and the normal is perpendicular to that tangent. To be able to find the equation of a tangent or a normal, you need two things. You need to have a coordinate pair, so you need to have an x, y coordinate. And the other thing that you need to know is the gradient at that point. The gradient at that point. Once you've got those two things, you can just use the formula y minus y1 equals m brackets x minus x1. So perhaps the best way to demonstrate this is with an example, and it's actually related to this graph we've got here. So this example says, find the equations of the tangent and the normal to y equals a half x cubed plus 3 over 2x squared minus 2x plus 1 and x equals 1. Well, the first thing I need is an x, y coordinate. So when x equals 1, I'm going to find out what the y value is. When x equals 1, y would be equal to a half times 1 cubed, which is just a half, plus 3 over 2 times 1 squared, which is just 3 over 2, minus 2 plus 1. So that is going to be, this is 2, minus 2 is 0, plus 1, and you get 1. So the coordinate pair is just going to be 1, 1. The next thing I need to do is to find out the gradient. So I'm going to differentiate this expression that I've got here so that I can come up with an expression for the gradient. So dy by dx, that's what y differentiates to, is going to be equal to, pull that power of 3 down, so you get 3 over 2x squared. Pull that power of 2 down, and 3 over 2 times 2 is 3, and reduce that power by 1. And 2x is just going to differentiate to 2. That x is just going to differentiate, it's just going to disappear. It's like that power of 1 going down to a power of 0. And that 1 is not going to be there at all. So now I know that x is equal to 1, I can find out what dy by dx is. So dy by dx, when x is going to be equal to 1, is just 3 over 2 plus 3 minus 2. So that's going to be 5 over 2. So then the equation of the tangent is just going to be equal to y minus y1, which is this bit that we've got here, equals m, which is 5 over 2, that's the gradient at x equals 1, x minus x1. Now the normal is going to be the same thing with the y minus y1 and with the x minus x1, except that we want the gradient to be perpendicular. And to find the perpendicular, it's going to be the negative reciprocal, which is minus 2 over 5. Now I haven't needed to tidy these up, but if you wanted to, you could make y the subject if you wanted to. And I've got this one, I put this on Desmos, so this is the equation of the tangent, and this one here is the equation of the normal. Now you can also do things like finding out the second derivative of something. You could also do the third, the fourth, whatever you wanted to. So if you take, if you take the derivative of y twice, unsurprisingly, you get something that is written like this. You get d2y over dx squared. Now, I guess the reason this is happening is because you're doing this d part twice, so that's why the 2 is kind of applying to that, and the dx part is also happening twice. Now, sometimes people say, oh, really, shouldn't we have brackets around that? But I think it's just that mathematicians have got lazy. Now, with function notation, if you differentiate something twice, it would just look like this. If you differentiated something 3 times, it would look like this. I guess if you differentiated something in this version 3 times, you just have the 3 after the d and then the 3 after the x. Okay, so let's see if there are some other applications that we can do with the second derivative. Now, the second derivative is telling you how the gradient is changing. It's like how we're saying it's the rate of change of the rate of change, or the rate of change of the gradient. And so we can relate that to this graph that we've got drawn here. Now, if the second derivative at a particular point is negative, we would describe the stationary point as a maximum, or a local maximum, I should say. And the reason why that's true is because as you move across the graph here, the gradient is very positive, it's then becoming 0, and then it's becoming negative. In other words, the gradient is decreasing. Now, the way I like to remember this is at this stationary point here, which is a local maximum, doesn't mean it's the biggest in the whole graph, but just in that area, everywhere you would look, if you were stood there, it would look like it was going downhill. It looked like it being negative, which is why I've said it makes me think of the second derivative being negative. If the second derivative is positive, the stationary point is actually referring to a local minimum. So I can add that on our diagram as well. So that would be down here. It looks like a minimum part of that graph. And the way I remember that is if you was kind of like stood on this point of the graph, everywhere you would look, the gradient is going upwards. And it makes sense because you have a negative, which is becoming 0, which is becoming positive. So in other words, the gradient is changing at a positive kind of rate. Now, if the second derivative is equal to 0, you actually have to investigate further because it could refer to different things. It could be a maximum or minimum, or it could be something which is called a point of inflection. Now, a point of inflection is like this example that we've got here. It's like when the curve is kind of swerving into different directions. So to do this, what you do is you check the value of the gradient either side of the stationary point. So in this case, if the gradient was positive and then negative, you've got a maximum. If it was negative and then negative over here, you have a point of inflection, or if it was positive and then positive. And if you have a negative and then a positive, you've got a minimum here. There are some things with optimization problems where you can maximize or minimize any function, which I'm going to do as this example problem. And I just want to do a quick note for people that are doing year 1. If you are doing chapter 14, which is on exponentials, you need to know how to differentiate them, but we cover it in much more detail in the second half of this video. But you do need to know that if a function is e to the x, then the first derivative of it is just going to be e to the x. It just differentiates to itself. And if it was e to the kx, so if there was a number in there, it would just differentiate to k e to the kx. So I'm not going to do too much on that. I think that's best to kind of leave with exponentials and with some of the year 2 stuff. So let's have a look at this example problem, which is going to be an optimization problem, but it's probably also going to pull in some things to do with, it's going to pull in some things to do with the second derivative as well. Okay, so going to look at, Okay, so this is an example of an optimization problem. It says here that the cost in C pounds of the chemical process is modelled by this formula that we have here, where T is the controlled temperature of the process in degrees centigrade. Using differentiation, find the temperature which minimises the cost, the minimum cost, and confirm by differentiation that it is a minimum. So it's asking us to differentiate this function that we've got here, and we're going to say that it's... Okay, so this example problem is an optimization one, and it's always about trying to make something a maximum or a minimum. So it says here that the cost in C pounds of the chemical process is modelled by this formula that we've got, where T is the controlled temperature of the process in degrees centigrade. Using differentiation, find the temperature which minimises the cost, find the minimum cost, and confirmed up by differentiation that it is a minimum. So you can see why people might want to use this kind of thing in real life to make things as cost effective as possible. So we're going to try and find the temperature which minimises the cost. Well, a minimum cost is going to be where there's a stationary point or a local minimum. So I'm going to start off by writing down that the cost is equal to 200 t to the minus 1 plus a 10th t plus 12. So I've just changed that first bit to make sure that it's written in that kind of standard form. Now I'm going to differentiate this with respect to t to find out that dc dt is equal to, well, I'll pull that minus 1 down, so I get minus 200. And I'm going to reduce that power by 1 to minus 2. The 10th t is just going to differentiate to the 10th. You kind of just get rid of that t there, and that 12 is just going to kind of disappear completely. Now, if it's a minimum, there's just going to be that dc dt has got to be equal to 0. So I'm going to make that equal 0 and then solve the equation. So that's minus 200 over t squared, because it's the power of minus 2, is equal to a 10th. Well, not equal to a 10th. Plus a 10th is equal to 0. So if I put the 200 over t squared on the other side, I get 1 over 10 equals 200 over t squared. And if I just come up here, that gives me that t squared is equal to 2000. And when you take the square root of 2000, you get 44.7 degrees centigrade. So this is the temperature which minimizes the cost. We're now going to find out what that cost is. So I'm just going to take that cost of 44.7 and I'm going to sub it back into this equation that we've got here. So I would do 200 over 44.7 plus a 10th of 44.7 plus 12 . And that gives us, to 2 decimal places, £20.94. So we've done those first two parts. It now wants us to confirm by differentiation that it is a minimum. So to confirm that something is a minimum, we're going to use the second derivative. And we're hoping, if it's going to be a minimum, that the second derivative will be greater than 0, referring to this minimum cost here. So I'm going to differentiate it again. So I'm going to differentiate, and I'm going to be differentiating this one right here. So I'm going to get d2c over dt squared. Well, this is going to differentiate with a negative times a negative. So I'm going to get a positive 400. I'm going to get 400 t to the minus 3. Now, this is pretty obviously going to be a positive value because when you substitute in a value for t, this is just going to stay as some kind of positive value. So let's just quickly work out what this is. So I'm going to sub in when t is equal to, when t is equal to 44.7, the second derivative is something like 0.0044, which is clearly greater than 0, hence it is a minimum. Okay, so that's everything that you need for year 1 differentiation. If you're doing year 2, then stick around and we'll see how we do that next part. Okay, so differentiation in year 2 has got all the same ideas from year 1, but they just add in more complex functions and then a couple of extra bits at the end. So let's just have a look at some of these standard results that will that you definitely should memorize. So the first one we already know how to differentiate. Ax to the power of n, we know from year 1 is just an x to the n minus 1. If you have an exponential function where the x is in the power, it stays as the exponential function, but you also multiply it by the natural logarithm as well of the base. E to the x will just differentiate to e to the x. ln x will differentiate to 1 over x. And now uv, this is where u and v are both functions of x. So you've got two functions being multiplied together, and this is the product rule. The way you do this is you take both of the separate functions u and v, you differentiate them separately, and then you multiply them in this way, so that you get u multiplied by v dash, and then you add u dash multiplied by v. So I use that little cross pattern to remind me of the product rule. The quotient rule is a little bit more complicated. So you do the same thing with u as the numerator and v as the denominator, and you do this kind of little pattern here. So that means that first of all, I want you to do v multiplied by u dash. The order does matter, so it's v multiplied by u dash, and then you subtract u multiplied by v dash, which is the second part there. And that is then divided by v squared. You need to know some trigonometry as well. So sine x is just going to differentiate to cos x, cos goes to minus sine x, and tan goes to sec squared x. Now, once you've got these ones here, you should be able to get some of the other ones. Oh, hang on a second. Sec x goes to sec x, tan x. These just need to be memorized, really. Now, anything that begins with a c just happens to end up as being negative. So cot and cosec are also negative, just like cos is. Now, to find cot, you look at the tan one and you So to find cot, you look at the tan one and you also add a co. So tan is the same as cot, but with a co. So we're just going to add in a co, so you get minus cosec squared x, and it's the same for cosec. You get the same as sec, but you just add co for both of these. So you get cosec x and then cotan, which is the cot x. So you need to make sure that you know how these ones work. Now we're going to talk about the chain rule. The chain rule is for when you have composite functions, and I'm going to show you the long version of it and then the quick version of it. So this right here is the chain rule, that if you have dy by dx, you can do dy by du multiplied by du by dx, and you decide that the inside function is called u. So let's have a look at this one that we've got here. It's definitely not something we could have done in year one. We've got this inside function and it's being raised to the power of 5. So what I'm going to do for this is I'm going to call the inside function u, which is 3x squared plus x, which therefore means that the outside function is just going to be u to the power of 5. So I'm going to figure out what these both parts here are. So I'll differentiate u with respect to x to get du by dx, and that's just going to give me 6x plus 1. And then I'm going to differentiate y with respect to u, which is going to give me 5u to the power of 4. So using the chain rule that we've got at the top here, I can say that dy by dx is going to be equal to dy by du, which is 5u to the power of 4, multiplied by du by dx, which is 6x plus 1. Now, it doesn't make sense to have u when you've been differentiating something that was in terms of x, so we're going to replace that u with what it originally was, which is 3x squared plus x, and that's all to the power of 4, and then 6x plus 1. So kind of the shortcut here is you end up differentiating it exactly how you'd expect. We pulled the power down and we reduced the power by 1, but the trick was that we also had to multiply by the derivative of the thing that was inside the function. But I don't ever really do the chain rule in this long way. I do this quick method for the chain rule. So I'm going to express it in some function notation because sometimes that helps people to see what's going on. So if I have this g function inside the f function, well, you just differentiate the f function exactly how you'd expect. So it would go to f dash g of x, but you also need to multiply it by the derivative of that inside function, which is g dash x. If you had 3 functions, so let's say you had h, which was inside g, which was inside f, well, you'd still expect the f function to go to f dash g of h of x, but you'd need to multiply it by the inside function, which was g of h of x. Well, that's going to be g dash multiplied by g dash h of x. But that also had an inside function, which was h of x, so we would need to multiply by the derivative of that, which is h dash x as well. I'm going to do a couple of examples with those later on. Some people like the way that I teach it with this inside part being called blah. Well, if blah was inside the function, you'd still differentiate it and expect you'd get f dash blah. Blah can mean any function at all. But at the end, you better make sure you multiply it by the derivative of blah. So you can see that here. This is blah to the power of 5. It's going to go to 5 blah to the power of 4 multiplied by the derivative of blah. Sometimes people find these little diagrams with boxes an easier kind of way of thinking about this. So if you have ln of anything, we know that ln functions always go to 1 over that function. And we can see that from over here, right? ln functions always go to 1 over whatever it is inside ln. But crucially, because of the chain rule, you need to make sure that you multiply it by that derivative, that extra derivative, which I'm just going to represent by this box with the dash. Now, sec functions, we know, always go to sec tan. And again, we talked about that one right over here. Sec x will go to sec x tan x. So if it had a different function inside x, it would still remain inside these places. But because it's the chain rule, you crucially need to multiply it by the derivative of that inside function. E to the power of anything is still going to differentiate e to the power of that same thing. It's the definition of the exponential function differentiating to itself. But crucially, you need to multiply it by the derivative of that power. And if you have a times something to the power of n, well, we know that that's normally going to go to a n, that something, to the power of n minus 1, but you also better multiply it by the derivative of that thing. And that's exactly what's happened in this question here. So let's also have a look at parametric differentiation. This one's actually really easy. It sounds like it's going to be hard, but it's pretty straightforward. So if y is a function of theta and x is a different function of theta, I guess I really should have called that g of theta instead. Then to find dy by dx, what you do is you differentiate y with respect to theta and you divide it by differentiating x with respect to theta. Just a little note about why this works. dy by d theta, if you divide it by dx d theta, you're really multiplying it by d theta dx, the reciprocal, and those d thetas are effectively cancelling out, so you do end up with that dy by dx. Now, implicit differentiation is when you want to differentiate something with respect to a variable that doesn't match it. So in this case here, we want to differentiate 3y to the power of 4, but with respect to x. Now, if we wanted to differentiate it with respect to y, that would be really easy, but we're doing it with respect to a different variable. So what you do is you differentiate it as would be expected, but you also multiply it by dy by dx. This is only if you're trying to do y with respect to x, okay? So let's just see why this works. I'm going to try and differentiate 3y to the power of 4 with respect to x. Well, that kind of doesn't make any sense. So instead what I'm going to do is I'm going to rewrite the question and I'm going to differentiate 3y to the power of 4 with respect to y. That doesn't really feel right that you can just switch these around. So the trick is this multiplying by dy by dx. If I multiply at the end by dy by dx, effectively what's happened here is I've got the exact same thing on the left-hand side as I do on the right-hand side, because these dy's are kind of sort of cancelling each other out. So we can now actually answer this question, because when you differentiate 3y to the power of 4 with respect to y, you get 12y cubed, and we've still got that dy by dx that we're multiplying by at the end. So that is a really, really quick overview of all the different functions you can now differentiate. We're going to dive in and try and answer these questions, and then we've got a tiny little bit at the end. Okay, so let's try and differentiate these with respect to an appropriate variable. So this is going to be lots of chain rule stuff happening here. So I've got 2 to the power of x squared. Well, from the chain rule, if I differentiate with respect to x, I know that I would normally get ln2 multiplied by 2 to the power of x squared. However, I also need to multiply by the derivative of this inside function, which is 2x. So I'm going to get this expression like this, and perhaps I could tidy that up and I will have 2x ln2 at the beginning. Let's write that this way. So I'm going to get 2x ln2 multiplied by 2 to the power of x. So we're going to try this one with respect to x, so it's going to be dy by dx. Now, ln functions always just go to 1 over x, and it's just being multiplied by 3, so it's just going to go to 3 over x. Obviously, that's because 3 multiplied by 1 over x is just 3 over x. This time, we have something that's in terms of theta. So I'll differentiate with respect to theta, that's dA d theta, and it's going to be the chain rule because I've got this 3 theta that's inside. So the 2 is going to stay there, but it's also going to multiply by the derivative of this 3 theta. So it's going to be a 6 cos 3 theta. That's because sine differentiates to cos, and then the derivative of the 3 theta is 3, which changes it to a 6. Let's have a look at the chain rule for this one again. Now, it's an ln function, and we know that ln functions always go to 1 over whatever inside. So that's going to be a 4x squared plus 2x plus 3. But because of the chain rule, we also need to multiply by the derivative of this, which is going to be 8x plus 2. So I can put it into that one fraction straight away. This is some tips for these question E and question F about how you can deal with trig when it has powers. Now, my tip for that is to rewrite it like this so that you have 4 tan of x cubed. So I'm going to take that 3, that cubed, and I'm going to write it in this kind of traditional way of actually putting it at the end rather than inside the function. Now again, it's going to be another example of a chain rule when I differentiate with respect to x. So I've got 4 blah cubed. Now that means normally when I have something that's just cubed, I pull the power down and I reduce the power by 1. So when I pull the power down, I get 12. I'm going to reduce the power by 1, so it's going to become tan squared x. But I also need to multiply by the derivative of that inside function, and tan differentiates to sec squared. Okay, this next one's going to differentiate with respect to t. I'm going to do that same thing, and I'm going to rewrite it in its other form. So that's going to be 2 brackets cos t to the power of 4. Now I differentiate this with respect to t. I'm going to pull the power down and reduce the power by 1. So it's going to become 8 cos cubed t. And now I need to multiply by the derivative of cos t. And cos will differentiate to minus sine t. Okay, so we've got v here. V is going to differentiate with respect to t. Now I don't need to do any expanding like I would have done in year 1. I can just dive straight in with this. So it's going to be dv by dt. I have got blah squared. That means pull the power down and reduce the power by 1. So I'm going to pull the power down, I'm going to reduce the power by 1, and then I'm going to multiply by the derivative of the thing that was inside the blah or the box. And the derivative of that is just going to be 12 minus sine t. Okay, this one is x and it's in terms of y, so I'm going to differentiate this with respect to y and get dx dy. I'm going to take the power and pull the power down because I've got 4 blah cubed. So that's going to become 12 blah squared. I pulled the power down and reduced the power by 1, but I also need to multiply by the derivative of this blah, which is just going to be 10y plus e to the y. Now, because I'm differentiating with respect to y, I didn't need to do implicit differentiation because it was in terms of y. Okay, let's have a look at this one here. It's y in terms of x, so I'm going to want to differentiate with respect to x. So I'm going to get dy by dx. Well, it's e to the blah, and I think this is actually going to be an application of a triple chain rule because there's a function inside a sine function which is inside an exponential function. So follow this one really carefully. Well, it's going to be an e, and it's going to stay the same. It's going to be a sine of x squared plus 4x. Now I have to multiply by the derivative of sine of x squared of 4x. Well, sine is going to go to cos, so it's going to be cos of x squared plus 4x. But I now need to multiply by the derivative of x squared plus 4x, and I'm going to put that at the beginning, which is 2x plus 4. So you can see you've got 3 pieces that's come from the chain rule being applied twice here. This is also an example of the chain rule being applied twice. So this is the sine of 3x to the half all squared. So the inside function is 3x to the half. It's then in a sine function and then it's being squared. So that's why the chain rule is going to need to be that kind of like double chain rule. So it will be dy by dx. I'm going to start off for this something squared function by pulling the 2 down and reducing the power by 1. So it's going to be 2 sine of 3x to the half. But I now need to multiply by the derivative of sine of 3x to the half. Now sine of 3x to the half is going to differentiate to cos of 3x to the half, but you need to make sure that you're also multiplying by the derivative of this, which is 3 over 2x to the minus a half. Collecting all these terms together, the 2 times 3 over 2 is just 3. So I have the 3, I have the x to the minus a half, I have the sine of 3x to the half, and I have the cos of 3x to the half. I've got now an example of something with the product rule. So I'm going to say that u is equal to 3 cos 2x, and v is equal to sine 4x. So when I differentiate these, u dash is going to differentiate to minus 6 sine 2x, and v dash is going to differentiate to 4 cos 4x. That's some application of the chain rule. So the product rule will say that the f dash x is going to be equal to these 2 multiplied added to these 2 multiplied. So that is 12 cos 2x cos 4x minus 6 sine 2x sine 4x. So you can definitely see these things becoming more complex. This one that I have here is also going to be an application of the product rule. So y is e to the minus x, sorry, u is e to the minus x, and v is tan 2x. When I differentiate this, well, it's going to stay as e to the minus x, but also multiplying by the derivative of minus x, which is minus 1. And tan 2x is going to differentiate to definitely a sec squared 2x, but also need to multiply by the derivative of 2x, which is 2. So putting that together with the product rule, we get that dy by dx is equal to, from this product rule over here, 2e to the minus x sec squared 2x minus e to the minus x tan 2x. We've now got an example for finding the quotient here, quotient rule. So in this case, u is equal to sine x and v is equal to x squared. Differentiate sine x and you get cos x. Differentiate x squared and you get 2x. And it does this pattern where you start off with doing the v u dash. So dy by dx is going to be v multiplied by u dash, that's x squared cos x, minus the other 2. So it's going to be minusing 2x sine x. And that's all divided by v squared. And v squared is going to be x to the power of 4. So just a reminder, that's just an application of the quotient rule that we've got over here. This can be simplified if you needed to. You can see that you could divide everything by x. so that the powers would become like this, leaving you with x cos x minus 2 sine x all over x cubed. Got an example of a parametric one here. So I'm going to start off by finding out what dx d theta is. 4 tan theta is going to go to 4 sec squared theta. And then I'm going to do dy d theta. Sec theta goes to sec theta tan theta, and that 2 is obviously just going to stay there. So dy by dx is the dy d theta divided by the dx d theta, which is what we talked about up here. So that is going to be 2 sec theta tan theta, all divided by 4 sec squared theta. A couple of things that you should notice happening is this sec theta will cancel with the sec squared, so it's just going to become a sec theta. The 2 over 4 is a half, so we get a half tan theta. The sec theta goes from the denominator to the numerator and becomes a cos theta. Now, because tan theta is sine theta over cos theta, we have sine theta over cos theta multiplied by cos theta. The cos thetas cancel, and this whole thing just differentiates to a half sine theta. Nearly there. An example of some implicit differentiation. So I'm going to differentiate everything here with respect to x because I want to find out dy dx. Just going to do each term one at a time. So x squared will differentiate to 2x. 3y cubed. Now this is y cubed and we want to do it with respect to x. So we do it as we would expect. 3 times 3 and pull the power down. So that's going to, pull the power down and reduce the power by 1. So that's going to be 9y squared, but because it's implicit, you need to make sure you multiply it by dy by dx. Now this bit here, you might like to do the product rule on here. So I'm going to jot down that x is equal to minus 2x, and that u is equal to minus 2x, and v is equal to y squared. That's just going to differentiate to minus 2, and because you're doing implicit here, this is going to go to 2y dy by dx, because remember you're still doing with respect to x. So the product rule will be these ones crossing over. So I'm going to get minus 2y squared, and I'm also going to get minus 4xy dy by dx, and 7 is just going to differentiate to 0. So all you need to do now is factorize the dy by dx. So you get dy by dx, 9y squared minus 4xy. I'm going to put the 2y squared and the 2x on the other side, so that dy by dx is going to be 2y squared minus 2x all over 9y squared minus 4xy. Okay, we're really nearly at the end here. We've just got a couple of applications of some of these things. So first we're going to talk about some reciprocals, then we'll do an example with connected rates of change, and then we'll finish the whole video with an exam style problem. So when I talk about reciprocals, all I'm saying is that dx dy is actually the same as just 1 over dy by dx. It just kind of makes sense that if you just flip the derivative, you can just take the reciprocal as well, and that applies for any letters, not just x and y. Now, when we're talking about connected rates of change, this is kind of like the applied problems that you might see here. If you ever look at an applied problem like this one that I've got written in black, and you see the word rate, rate means that something is happening with respect to time, so you can translate that into something dt. So what you do in these questions is you express what you are looking for in terms of other derivatives. So if you're looking for something like dA by dr, you could do that by trying to split it up into 2 other rates of change that are connected to each other, hence the title. All you need to do is just fill in the blanks with another variable that appears in the question. Usually that's going to be something like dt. And what you can notice is that these 2 things are actually equivalent to each other because those dt's are cancelling. The best way to explain connected rates of change is really just to do an example. So it says here that the volume of a cube is increasing at a constant rate of 5 centimeters cubed s to the minus 1. This means 5 centimeters cubed per second. Assuming the solid remains a cube as it grows, find the rate of increase of the side length x centimeters when x equals 2. Well, the thing that they actually want me to find in this question is the rate of increase of the side length x. So they want us to find out what dx dt is, the rate of x. That's what I'm going to try and find out. So I'm going to do as I advised up here, and I'm going to split it into 2 different fractions, a dx d something and a something dt. I'm also going to pull out some of the information from the question. So they've said that the volume is increasing at a constant rate of 5 centimeters cubed per second. So that must mean that dv dt, the volume is changing at a rate of 5 centimeters cubed per second. The clue in the units being centimeters cubed for volume per second for time. And we also know that it's a cube, right? So we know that, let's just put this over here. We know what the volume of a cube is. We know that the volume of a cube is the side length cubed. So if I differentiate this with respect to x, I get that dv by dx is equal to 3x squared. Now I think I've probably got the idea of how to fill in these blanks. I've got x, I've got t. I think these missing parts are going to have to be dv. So I'm going to say that this one is going to be dv and this one is going to be dv. Well, dx dv, I don't have that. I have dv dx, but because of what I mentioned up here about reciprocals, I can just flip this over. So instead of it being 3x squared, dx dv is 1 over 3x squared. And dv dt, we wrote down here from the question, is just equal to 5. So it's equal to 5 here. So this is 5 over 3x squared. But they want us to know what is the value of that dx dt when x is equal to 2. So I can say if x is equal to 2, then dx dt is just going to be equal to 5 over 3 times 2 squared, which is just 5 over 12. And the units for that are going to be centimetres per second, because it's centimetres for x divided by time, which is seconds. Last part is thinking about second derivatives. Now, we talked about second derivatives referring to local maxima and local minima, but we now in year 2 add in this idea of something being concave or convex. So concave on a diagram is referring to this first section that we've got here, and my sort of silly way of remembering that it's concave is I imagine that this sort of looks like a cave. Here's the entrance to the cave with like a silly pathway. I mean, I just say it to my students and they seem to remember it. Now, you'll remember that if it was a local maximum like this, the gradient was negative on either side. So we could say that it is concave. Sorry, the gradient isn't negative on either side, but that was my way of trying to remember it. So it is concave if the second derivative is less than or equal to 0. Now, some people say less than 0, some people say less than or equal to, but you won't be penalised for this, for Edexcel especially. It is a convex, which is the other part. This section here is all convex. That makes me think of the V in convex. I know concave has a V as well, but convex, I think the V is more pronounced. So this section here is convex. I guess I should have labelled this as concave, and this is convex. And that is going to be if the second derivative is greater than or equal to 0. Like I said, it doesn't matter which inequality sign you use, greater than or greater than or equal to. And then we've got this point of inflection. Now, in year 1, when we talked about a point of inflection, we talked about a point of inflection that actually happened to have a 0 gradient right here. Now, a point of inflection doesn't have to have a 0 gradient. It's actually where the curve is swerving from being concave to convex. So I would say that that point of inflection is exactly here. This is our point of inflection. Now, when I explain this in my videos, I talk about if this was a bird's eye view of like driving along a road, at a point of inflection, your steering wheel would be completely straight. So at a point of inflection, the second derivative is equal to 0. A little side note though, a point of inflection implies that the second derivative is equal to 0. However, if the second derivative is equal to 0, this does not necessarily mean that it's a point of inflection. What this actually means is that it could be a point of inflection, it could be a maximum, it could be a minimum. You would have to investigate by checking dy by dx either side of it. Okay, I'm going to finish this up with one last exam question, and it's one that focuses on some stuff that maybe hasn't been covered that much. It's on some things to do with implicit. So let's zoom in on this and see what's happening in this question. It says exam style problem. So the figure shows the curve with equation y cubed plus 3xy squared minus x cubed equals 3. First of all, they want us to find an expression for dy by dx in terms of x and y. Well, that should be pretty straightforward. I'm going to take this y cubed plus 3xy squared minus x cubed equals 3, and I'm just going to differentiate that down here and hopefully come up with dy by dx. So remember, anytime you differentiate y with respect to x, you have to add in a dy by dx. So you're going to get 3y squared dy by dx, and I'm going to do the product rule. I'm going to try and do this product rule just in my head. So I'm going to differentiate the x part, which is just going to give me 3, keep the y squared, and then I'm going to differentiate this y squared, which is going to give me 2y dy dx. So there's going to be the 3x and the 2y, which is going to give me 6xy dy by dx. Minus x cubed is going to go to minus 3x squared, and when you differentiate 3, you just get 0. So I'm going to factorize the dy by dx's. So it's going to be dy by dx, 3y squared plus 6xy and I'm going to put the other terms on the other side so that I get 3x squared minus 3y squared. So just dividing through, we get that dy by dx is equal to 3x squared minus 3y squared, all divided by 3y squared plus 6xy. Now, I think this can be simplified, right? So if I simplify this by dividing everything by 3, I get that dy by dx is just x squared minus y squared over y squared plus 2xy. So we've done part A of this question. We found an expression for dy by dx in terms of x and y. Part B of the question says that vertical tangents are drawn at A and B as shown on the figure. Determine the coordinates of A and B. Okay, well, I think A is going to be really easy to find out the coordinate because you can clearly see from the graph that at A, the y coordinate is equal to 0. So we just need to find out the x coordinate. So when y is equal to 0, I'm just going to sub it into this. I'm just going to get 0 plus 0. So I just get minus x cubed equals 3. So that means that x cubed is minus 3. In other words, x is the cube root of negative 3. Now you can take the cube root of negative 3 and you can either say that it's this, the cube root of negative 3, or that's just the negative cube root of 3. So the coordinate of A is just going to be the x coordinate, which is minus the cube root of 3, and the y coordinate, which is 0. Now, B is going to be a bit trickier to find, and it's actually to do with the fact that it has a vertical tangent. Now, when something has a vertical gradient, we mentioned this right at the beginning of the video, it means that dy by dx is undefined. And we need to think about how we can make dy by dx being undefined. So I want to have a look at this expression and think, how can it be like that? Well, something is undefined if the denominator is equal to 0 because you're therefore dividing by 0. So I'm going to say here that dy by dx is undefined when the denominator is 0. Is undefined when, and in this case, it's going to be y squared plus 2xy is equal to 0. So to solve this and find out what y is equal to, I'm going to factorize. So I get y brackets y plus 2x equals 0. Well, this looks like it gives me two solutions. It either gives me that y is equal to 0 or that y plus 2x is equal to 0. Well, this y equals 0 has actually already given us the a coordinate. So I'm just going to continue investigating with this one. So y is equal to minus 2x. Well, I've now got two equations. I've got this equation and I've got the original equation up here. All I need to do is just solve those simultaneously and see what we come up with. So, subbing that into the y cubed one that we've got at the top, I'm going to get minus 2x all cubed plus 3x multiplied by y squared, which is going to be minus 2x squared, minus x cubed equals 3. So minus 2 cubed is minus 8. I've got 3 times minus 2 squared, which is 12, and I've got x times x squared, which is x cubed, minus x cubed equals 3. Simplifying the left-hand side, that's going to just give me 3x cubed equals 3. X cubed equals 1, which means that x is also equal to 1. And because we know that y is equal to minus 2x, y is equal to minus 2. Hence, the coordinate of B is going to be 1 minus 2. Does it look right on the diagram? Yep. It is 1 minus 2, and that one does look like it's in the right place as well. So I think we've answered that question pretty well. Okay, there was a lot of stuff we've covered in this video, but it is a huge topic and it's a very, very important one. So see if you can answer some of these after you've watched it, see if these still get the same answers. Okay, I recognize that was a really, really big video, and if you've got to the end of it, very well done. If you haven't subscribed to my channel, do make sure that you go there and you hit the subscribe button. If you want help on other topics, I've got one of these on trigonometry, there's some stuff on integration, and there's, as I said before, all the tutorials for all of the different topics. So just wishing you the best of luck with all of your studies, and I hope that things go well for you. Good luck.